Yeah. Yeah. Yeah, you don't. Just I'm going to have a few comments today before our test on just finishing up the stuff we were talking about at the end of last lecture, quantum bomb detector, and some brief introduction to multiple qubits. Very brief. I know it's Friday and you're all anxious to get to the test, so we will just keep it fairly short, but just to get us started on the next part, and then we'll go to the test, which I don't think will take you too long, but it's fine. We'll make sure you have plenty of time. Okay, let's get started. Yeah, that's just outline. I already mentioned that. Okay. And okay, so this is just quick. Just paging through the slides that we went through at the end of last class. If anybody has questions, feel free to stop me at any point. So again, Ellipser-Weidman bomb problem. We need to pick out which boxes have working bombs and not detonate them. Okay? And this was our first solution where we sent in the plus state. We decide whether, you know, if there's an explosion, basically you can think of it as if there's a measurement result, right? When the Turing machine measures the qubit, it gets a 0 or 1. So if it gets a 1, then it blows up the bomb. And then if not, then in this version, we immediately measured the state in the plus or minus basis. And then we had two possible results. Yeah.
So the way you get a minus state in the after, so are we assuming that if there's a Turing box, it alters the state you're sending in?
It has to, right? Okay. Because a Turing machine is a classical machine. And a classical machine only knows 0 and 1. It doesn't know superpositions, right?
Oh, yes, I can.
Yeah. Right. But we know quantum mechanics, so when the state comes out, we can decide to measure in a rotated basis. Okay? Or rather, Q can. Okay, that's just a summary of the last time we went through this. Okay, I'm not going to go through that again. It was from a few lectures ago, just summarizing over there. And our goal was to improve the detector. And we did that by, as suggested by somebody in the class, this is the exact same idea at one point, which is to define a new basis, which is called U and V. Okay. And it's also orthonormal, just like plus and minus are orthonormal basis set. But the difference, and you know, now that we know how to write the gate that transforms from one basis to another, we just write it down in one line, like that, right? And you know now what that means. You can write down the linear algebra expression for it by taking the column vectors and row vectors and multiplying them. And in the block sphere, this U and V, the way we are picking them is they are a small rotation by epsilon around the y-axis in the block sphere from the 0-1 basis set. Okay. So X and the plus and minus states would be 180-degree rotation. Although it looks like 90, remember from your assignments, you should know that a 180-degree rotation basically corresponds to that X and Y basis. So, sorry, 90-degree. Whatever. 180 will take you from 0-1 to 1-0. Apologies. Okay. So, right. So yes, so the small rotation we wrote as this set, and I'm going to prove to you that this is indeed a rotation by a small amount epsilon around the y-axis. That this basis is what you'll get when you rotate by epsilon around the y-axis. Okay, we'll show that in a minute. But epsilon was picked to be an integer fraction of pi. Okay, and the way we prove it is by just referring to the general result. This is the general result for any qubit gate. Okay, any general qubit gate around some axis is a rotation about some axis nx, ny, and z, and by an angle theta. So can be written in terms of the gates I, x, y, and z. Okay. And now we have the linear algebraic expressions for I, x, y, and z. They're just matrices. So we can just substitute in and find the actual element. So U was written as some e to the I gamma times cosine theta over 2 times the identity matrix minus I sine theta over 2 times nx x plus ny y matrix plus nz z matrix. Okay. So for a rotation, let's set for now gamma equal to 0. We can always change it later if we have to. And we set theta equals epsilon. Okay. And this is a rotation around the y-axis. So nx equals 0, ny equals 1, and nz equals 0. Right? Rotation around the y-axis. So from all this, we then get it's equal to cosine theta over 2 times the identity gate minus I sine, epsilon over 2 minus I sine epsilon over 2 times the y gate. Okay. And the y gate is just 0 minus I 0. Okay. Therefore, we get U equals now for I and the I identity gate is of course just the identity matrix. We get now cosine epsilon over 2. So now I'm multiplying cosine epsilon over 2 into the identity matrix. So I get a matrix which is cosine epsilon over 2, 0, cos epsilon over 2. Okay. Then over here, I get minus I sine epsilon over 2 times this matrix 0 minus I 0. Okay. So I'll just focus on this matrix. So I'm multiplying out minus I sine epsilon over 2 into this matrix. So I get minus sign, or let's take this as plus and take minus I inside the matrix. Okay. So or minus I sine epsilon 2 over 2 inside the matrix. So this on this side is just cos epsilon over 2, 0, 0, cos epsilon over 2. plus there's 0 here, and then there's minus I times minus I. That's a minus sign overall, because it's like I squared is -1, so that's like multiplying 3 minus signs. So that's -1. So that's minus sine epsilon over 2. Okay. And then we get sorry, where was I? Yes, here. Minus I times minus times I. Well, that's going to be +1, so that's sine epsilon. Good. And so and then 0. So the end result is cosine epsilon over 2 minus sine epsilon 2 sine epsilon over 2 and then cosine epsilon. Now, unless I messed up the definition of the y gate, it's possible. 0 minus I 0 or 0 I minus I 0. That is a phase convention that are always different books have different phase conventions. So I should have checked that first. Probably have it in the PowerPoint. Let's go back one step. Yeah, I think it's correct. Okay, so now how do I know it's correct? Well, let me consider the state U. Okay. I claim that U is obtained by taking this. Sorry. By the way, I guess later in the slides I have called this the gate R. So instead of calling it U, I'm going to call it R. Just to be consistent with my own slides. Okay. Call this R. Pop the screen again. The gate U, I mean the state U, I claim is a rotation of the 0 state, right? By this rotation gate R. Okay, so let's verify by the matrix multiplication. So it's cosine epsilon over 2 minus sine epsilon over 2 sine epsilon over 2. So times, now what is 0 in matrix algebra or linear algebra? What does the state 0 look like? Yes.
1 0.
1 0. Okay, so you do the matrix multiplication, you get cosine epsilon over 2 times 1. So this is the column vector, cosine epsilon over 2 sine epsilon, which means that its components along the 0 and 1 states are cos epsilon over 2 sine epsilon over 2. Similarly, you can verify for yourself that the state V is indeed cosine minus sine epsilon over 2 cosine epsilon over 2. Okay. Any questions on this? How we got this result? Before I cover it up. Did everybody follow those steps? Okay, that is just the math. And the math just shows that indeed I have defined these new basis states U and V by the action of the rotation. Okay, all right, let's solve that. Okay, and now we come with the new protocol. This is our improved protocol for the quantum bomb detection. Our claim is that this protocol will allow us to make the probability of an explosion as small as we like. Okay, to nearly 0 if we want. Okay, and when there is no explosion, we can perfectly differentiate, near perfectly differentiate between bomb and Dutt cases. Okay, so let's look through the protocol. It looks very identical to the protocol that we had for the original quantum bomb detector. But now what we're doing is, first of all, we're sending in a new state, not plus state, but the U state. Okay. And we then again, explosion, which is equivalent to measurement by the Turing machine, right? They're the same thing. Okay. So, and then if we have a bomb, of course, I mean, if it explodes, then we are done. Okay, we have no option. The bomb is exploded. But if we don't have a bomb, that is, if we don't have an explosion, that means we rotate again. Okay, n times. We repeat this protocol n times. Okay. At the end of those n times, assuming no explosion on each of the trials or on each of the rounds, then we measure in the UV basis. Okay. And the question is, did you get one? If so, we claim that's a dud. If no, we claim it's a bomb. Okay, that was our claim. So let's go through the reasoning again. First of all, though, you may be wondering, how do I measure in any other basis U and V? Okay, I know how to measure along 0, 1. I never told you how to measure along plus minus, but I said, yeah, we can. And also we can measure along plus I minus I, right? In Ket algebra, we certainly know how to do it, right? We can certainly just go back to this state here and say, take the bra U and take the inner product of the bra U times the state psi. Okay, that's always allowed, right? That gives you the overlap between any qubit state and the basis state. You take the bra and you project it with the inner product onto the state side. That's what we call that, right? That component and the norm squared of that component gives me the probability to be in the state U. Okay. So that's one way to do it with Ket algebra. The other way, with our linear algebra and our gates knowledge, the knowledge with gates, we know that R dagger times U must be 0, because we just showed over here on the board that R times 0 is the state U. Okay, and R times 1 is the state V. Okay, therefore, if I operate with R dagger, remember R is unitary, so R dagger is its inverse. So we can operate from the left by R dagger, which is similar to something we did in the last class as well. Then you can just say the inverse of U through the rotation. If I undo the rotation with R dagger, I'll get back the state 0, right? If I do a rotation and get into state U, if I undo the rotation, I must come back to the state 0. And R dagger is the undo operation. If you remember, I told you that last time. For all unitary matrices, R dagger is like undo. Okay. All right, so that's all it takes then. In the quantum circuit language, what we will say is we'll create the state R. We'll rotate the state 0 with R. We'll send it into the Turing machine, which we could call as a measurement device of some type, and then at the end, we'll do, after n rounds of this protocol, we will operate with R dagger. Okay. And R dagger will take U states into the 0 state and V states into the 1 state. So measurement of 0 or 1 will tell us whether it is a U or a V state. Is everybody okay with this? Okay. So let's verify it for the Y basis. That is, now I'm taking I could have taken this. Maybe I should take this. All right, let's do it. Why not? I'm making this up today, so if I make an arithmetic mistake, it's on you to spot it. I thought I'd do it with the U basis because it's numbers rather than cos and sine epsilon over 2. All right, let's just do the Y basis, and then I'll leave it as an exercise to do the cos epsilon over 2 sine epsilon. It's the same thing. It's just extra. I'll have to keep writing cos epsilon over 2 sine epsilon. So, all right. So let's take the Y basis. So I want to make measurements in the Y basis. Yeah. If you illustrate with this, maybe it will become a little easier to understand the UV basis. Okay. So my statement is, if I take any state psi, okay, all right. If I want to measure its component along the Y basis, well, of course, I just take this, right? I do plus I. Okay. And the probability then to be in this state is the norm square of that border. Okay. But now I'm saying a different way to do the same thing is to take the state psi and send it through R dagger. Okay, to the gate R dagger. And I claim that the column vector that results gives me the projection of psi onto the y basis. Okay. What is R? R dagger? Well, R dagger is simply the state that is giving me, takes me from the basis, Z basis. Z basis, remember, is our 0, 1 states to y basis. And the y basis is the states plus I and minus I. Okay. I'm just doing this for the y basis, but you can follow the exact procedure for the z basis, for any other UV, for example. Okay. So first I need the matrix that takes me from the 0, 1. So let's find the matrix R that takes me from 0 to plus I. Okay, so first I find that matrix. Okay, and of course it should also take 1 with that same operator R to minus I. I need this gate. Okay, R which takes me from 0 to plus I and which also takes 1 to minus I. Very straightforward. I can again use that same formula, or by intuition, we can say, okay, so that R gate must be 1 I 1 minus I. 1 over. I claim that this is the gate, and we will verify it. Okay. So R acting on the state 0, okay, is 1 over root 2, 1 I 1 minus I, acting on the column vector 1, 0. Okay, and this, as you can see right away, gives me 1 over root 2, 1. Okay. We could have also said this gate must be written as using outer product language. This R must be plus I 0 plus minus I 1. Okay, so same thing. All of these are just different ways of saying the same thing. Okay, and I gave you Python and Mathematica code last time, so you can explicitly verify these outer products, or you can do it by hand, etc., etc. Okay, and similarly, R acting on 1, on 1 over root 2, 1 minus 1 minus I 0, 1 will give me 1 over 1 minus. Okay. Right. So we've shown that this gate R indeed does what we need. It takes us from 0, 1 to the y basis, from the z basis to the y basis. So now let's make sure that R dagger indeed takes us the other way. Okay. So R dagger is now, I have to take the states, so I have to take this and I have to take its complex conjugate transpose. So 1 and minus I stay there, but the minus I becomes plus I, right? The diagonals stay the same, and the off diagonals get transposed and conjugated. So this is R dagger. Okay. And now R dagger acting on the state plus I is equal to 1 over root 2. Is equal to 1 over root 2, 1 minus I, 1 I, and now acting on the state 1 I, 1 over root 2. Okay, that's the plus I state. So then we see that this must be 1 over 2 times 1. Yes, 1 minus I squared, right? So minus I squared is the same as plus 1. And then here it's 1 plus I squared, which is 1 minus 1. So that's 1, 0. Okay, and similarly, you can do it for the other state. R dagger acting on minus I will give you the 0, the 1 state. Okay, so this is a 0 state. Sorry. Okay, any questions about that? Let's finish up our story finally for this protocol. Now we know any general basis is the same idea. You just write down R, find R dagger, and do the same operation, and you'll get it. Okay. So if I first go through the protocol, but without looping n times, set n equal to 1, okay, which means, well, n equal to 0, so no loops. Okay, just go through without any loops first. Okay, we apply R to 0 to prepare the U state. Okay, in the first box in the protocol was send in the U state. How do I send in the U state? I take the 0 state, I operate with the R gate, and I get the U state, and I send it into the Turing machine box. Okay, and then the idea was if it's a dud, nothing happens to the qubit. Okay, there's no measurement, nothing. So it exits as the same state. If we measure in the U basis, of course, we're going to get back U, right? Because it was U to begin with, and now if I measure right at that point, it'll be U again with probability 1, right? But if it's a bomb, now the Turing machine has measured the qubit, and it has found it to be either 0 or 1, okay? And if it's 1, then there's an explosion, and that probability, this is the 0 state, okay? First we'll 0, which is just probability of finding 0 from that U state, which is just proportional to the amplitude along the 0 state, which is cos epsilon over 2 whole square, okay? Which is also pretty close to 1, okay? It's not perfectly 1 because epsilon is some small number, but it's close to 1 because any cosine of some small angle is close to 1, okay? What is the probability of explosion? Well, that's just probability to measure 1 in this state, okay? So sine epsilon over 2 whole squared, which is approximately, because we don't want to make it equal to 0, we want to estimate what this probability is. That probability is epsilon squared over 4. It's close to 0, but not quite, okay? Okay, so of course, like I said, if you go back to the protocol, if you explode, you're done, right? The protocol ends right there. But if you don't, and we measure in the UV basis, then we are going to find this answer, okay, with the probability. So we're just going to repeat that n times, okay? So the main thing to just understand is it's actually very simple. I mean, I can just explain it right here, okay? So the idea is that if I send in U and I measure into 0 state, what comes back here is either 0, right? And not 1, because 1 means explosion, so it's gone. Okay, the protocol has ended. But if it's a 0 state, again, it's basically like I reset my whole process back to the beginning. Okay, so again I send in U. Okay, each time I send in U, okay, if it's a bomb in there, every time it'll measure 0. It has to measure 0 because nothing happened, right? There was no explosion. So nothing happening means everything has reset back to the beginning. And we just rotate each time by the same amount, which is epsilon over 2, right? And therefore, we get back the state U every time. So after n rounds of the protocol, we'll still be in the state U if we did not get an explosion. So if I measure in the UV basis, I must get U because that's what we sent in and there was no explosion. Therefore, nothing happened to the state. So if it's still in the U state, okay, right? That means that it was constantly measured so that it remained in the 0 state. Each time it remained in the 0 state and got sent back. So the fact that it came out as U tells me right away that it's a bomb. Okay, because U, remember, is 0 in our basis. It's a 0 state. Okay, and what happens if it's a Dutt? Well, if it's a Dutt, remember the qubit basically is rotated by epsilon and gets sent back here. So the second time it gets rotated again by epsilon. After n times, it has rotated by n epsilon. Because it's a qubit, it remains in this qubit state. Okay. So that qubit state of u is now rotated n times by the angle epsilon, or starting with 0, it's rotated by n times epsilon, but epsilon is pi over n. Therefore, the total rotation is pi. So the qubit has started in the 0, 1 basis and ended up in the 1, 0 basis at the end. Okay. And so now measurement of 1 will give me proof that this is a Dutt. There was nothing in the box. Because if there was something in the box, each time it would have measured either 0 or 1, and I would have only gotten the U state. That is the initial state, that little one that was rotated by epsilon small amount. Okay. But every time, if there was a Dutt, nothing happens, the qubit rotates into the 0, 1 basis. Okay. So that is the final result. And so that is why if I get a 1 state at the end, that gives me that this is a Dutt, and if not, it gives me that it's a ball. Okay. Okay. All right. So that's the basic result. Everything else here is just calculation. So I'm not going to go through it again. We went through it at the end of last class. The point is that the only thing we need to know is what's the probability that there's an explosion. Well, remember, because each time it resets to 1, right, or resets to 0, the only problem would be if I measured 1 on any of the n rounds of the protocol. Okay. And what's the probability to measure 1 on any of those n rounds is the probability that I measure on 1 round times the number of trials, which is epsilon squared over 4 times n. Substitute for epsilon, we get phi squared over 4n, which is always lesser than this number, 2.5 by n. Okay. And that is our final result, that our probability for explosion is always bounded by this number 2.5 over n. And we can make that as small as we want by increasing the number n. For say n equal to 1000, this means that it can be made less than 0.25%, which going back to our old, the first version of the protocol, this was 25%. So we have reduced it by a factor of 100 already. Okay. Okay. Any questions? I'll think about it some more. This is a very interesting protocol because in a way, what I've just shown you, this idea is all that is there at the heart of quantum computing. Okay. Everything that I've said here is basically going to be implemented with multiple qubits and different things happening inside those spaces in those boxes. But everything else, the basic idea is rotate to some new basis, UV, right? And at the end, undo the rotation and measure. Okay. And this is going to be throughout all of the quantum computing protocols. So this simple bomb problem is kind of like at the heart of quantum computing. It's like it's this protocol will be followed in every quantum algorithm. Okay, rotate, do something. Okay, in this case, it was a classical measurement by a Turing machine. Okay, but in other cases, it will be some more fancy gates that we'll talk about. But in the end, undo the rotation and measure, and everything will magically somehow, like this problem, magically, we were able to make, a perfect bomb detector, starting with a situation where there was no hope, right? In the classical world, if you only knew classical mechanics or physics, there was no hope for solving this problem. And yet, by this quantum protocol, we essentially solve the problem. Okay. With some small probability of error, but okay, that's part of the thing with quantum physics. Now, I should mention, of course, the real world problem with this experiment, if you want to carry it out experimentally, is this qubit has to remain in the same state throughout the n rounds of the protocol. So that is a big real world problem. That's a separate issue. In terms of like theory, we can certainly say we understand how to solve this problem. Okay. And of course, you should ask, what about measurements? Can the measurement be imperfect? Then what happens? Yes, all of these have to be taken into account, right, for a real world demonstration. But the basic idea is this. Okay. So just remember that idea. Rotate, do something, undo the rotation. This whole simple in these words, what I just said, but just taking it now to like multiple qubits, and then eventually with gates and so on, quantum gates will be what we do in every quantum algorithm. Okay, that's basically it. We only know this one weird trick. Okay, so that's just a summary for linear algebra. Okay, I think I went a little bit longer than I had expected, so I'm not going to get into multiple qubits today. We'll do it in the next class. And let me just hand out your this.